This is Joe narrating a PowerPoint in science. It's from the unit on physical science, lesson 4, the nature of energy, found on page 548 in the Kaplan book. Some vocabulary. Energy is defined as the capacity to do work. Work is done whenever a force, which is a push or a pull, is applied to an object to set it in motion. We'll talk about the law of conservation of energy, which says that energy can neither be created nor destroyed, but it just changes form. Those forms of energy include heat energy, light, chemical energy, nuclear energy, and mechanical energy. We'll talk about another way to classify energy is as either kinetic energy, which is the energy of motion, and potential energy, which means the possible energy that you can get out of an object due to its position. How do we measure energy? We measure energy in a unit called joules. The scientific unit for energy is joules, but there are many other forms used. For example, calories is used to describe the energy in food. Power is defined as the energy used per a time period. For example, your light bulbs are marked in watts. That's how much energy they're using in a certain amount of time. And the bottom paragraph on page 548 talks about Einstein's famous equation E equals mc squared. The E stands for energy, m stands for mass, and c is the speed of light, which is a very big number. So this equation tells us we can get an awful lot of energy out of a small amount of matter. So thermodynamics is the study of energy and its transformations. There are three important concepts. Each of these is talked about in the book. Work is done when a force is applied and an object is moved. This is the physics definition of work. So unless something moves, there's no work done. Energy is the ability to do work and measured in joules, as we said. Power is a measure of how quickly work is done. And as we said, that's measured in units called watts. Here are some forms of energy: heat, light, sound, electricity, and the kinetic energy of movement. Then you can have stored or potential energy. For example, if you compress a spring, when that spring is allowed to release, it can do work. So the compressed spring has potential energy. Same thing if you have an object above the ground. When you release it, it can land and do work. The law of conservation of energy says that energy cannot be created or destroyed. It just can be changed from one form to another. For example, in order to ride your bicycle, you need the chemical energy that's in food. In order for a tree to grow, it needs the energy from the sun. Energy conversions. Here's an example of how potential energy in water at a higher level than a turbine can convert energy from one form to another. For example, we generate electricity in hydropower plants by having water fall through a pipe. This falling water turns a wheel at the bottom here on the right. That wheel turning turns a magnet inside a coil of wire, and that generates an electric current in the wire that is then sent out to your house. So then you can use that electricity to power your TV or your toaster. Potential energy is the energy of a position. So if you raise a ball up higher than the ground and you release that ball, when that ball lands, it can do mechanical work. So it can crush a can, it can make something rise in the air if it hits a lever. So you're converting potential energy into the kinetic energy of the moving ball and then into mechanical energy when it hits the ground. Here's another example. A hammer raised over a nail has potential energy due to its position. As soon as the hammer starts to move down towards the nail, it has kinetic energy, the energy of motion, and then when it strikes the nail, it is doing work on the nail. by making the nail move through the board. Likewise, an arrow has potential energy when it's drawn back in the bow, and when it's released, it has kinetic energy, and that arrow can do work whenever it strikes an object. A joule is a unit of energy, just like a meter is a unit of length. Other common units of energy are calories and BTUs. Power is the rate of doing work. If one person can lift an object faster than another person, we say that person is more powerful. There are some traditional units of power. One is horsepower, which is very complicated, but it is still used to describe the power of automobiles. And the more common one is watts, and the official scientific one is watts. That's the use of 1 joule per second. So it's a measure of how much energy you're using in a certain amount of time. And you see this on your microwaves, which generally run around 600 watts, and your light bulbs, which go anywhere from 25 to 100 watts. For example, this is showing the way horsepower is described. So you need a horse, you need a weight, you need a stopwatch, and you need a measurement of how much the weight is moved. So, for example, 1 horsepower is described as moving 550 pounds up 1 foot in 1 second. So again, a very complicated description of a unit of power. The last paragraph in the book talks about Einstein's equation, E equals mc squared. This equation says that matter and energy can be converted between each other, so that matter has the potential for releasing energy, and energy even has the potential to form matter. Because the speed of light, c, is so large, it means there's a lot of energy in even a small amount of matter. This equation was harnessed to develop the first atomic bombs, which were used only twice in the world, in 1945. This is a diagram of an atom bomb where uranium is, the nucleus of uranium is separated in the bomb to form 2 other elements. When that happens, the products of the reaction have slightly less weight than the reactants in the equation, and therefore the matter that is missing is converted into energy. This energy is substantial because even though only a small amount of matter is converted into energy, by Einstein's equation, E equals mc squared, this energy output can be enormous. This is a test of the atomic bomb in the South Pacific. That's it for page 548.